SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall discuss about the nozzle efficiency and then shall identify several factors those affect the nozzle efficiency. Now, if we try to recall, in this module of this course we have discussed about the nozzle in detail, starting from the flow analysis through the nozzle. We could establish the design aspects of the nozzle. So, when there is a flow through a channel, whether the shape of the channel or the flow configuration is convergent type or it is having a shape of convergent divergent type or it is of divergent type, we need to our basic objective. So, if we try to write the flow of steam through nozzle. So, if we consider a flow of steam through a duct having shape like this, this is section 2.2, this is section 1.1, and we are assuming that the walls of this duct are insulated. So, there is no heat loss. So, we are assuming so this is the flow direction. So, we are assuming that the walls of the duct are insulated and there is no heat loss. What is the basic objective of having this particular device for the operation of the steam power plant? We have discussed that the steam which is produced in the boiler or steam generator, that steam should be taken to the turbine for generating or producing work. Now, when steam is allowed to go into the turbine, it is allowed to pass through the nozzles and then steam jet which is coming out, rather I shall say the steam which is coming out from the nozzle in the form of jet strikes the turbine blades, and when there is a deflection of the steam jets, there will be a change in momentum. In fact, there will be a loss of momentum and that momentum will be absorbed by the wheel of the turbine runner. So, the basic objective of having this flow nozzle is to produce steam jet. That means, the steam which is coming out at the exit of the nozzle will have velocity which is, rather the velocity should be good enough so that the jet will be having high kinetic energy before that jet strikes the turbine blades. So, now why I am discussing this particular aspect again, because you know it is again a mechanical device. So, while someone is designing the steam nozzle, the designer must be careful to careful about the efficiency of the nozzle. So, why not to look at the efficiency of the nozzle, as by knowing this particular parameter we can predict what would be the kinetic energy or available kinetic energy of the jet at the exit of the nozzle. What is happening over here? So, as the steam is passing through this particular duct of this particular shape, that is initially we are having decreasing area, then again it is increasing gradually. So, area is increasing gradually. So, you know that at the inlet the conditions are velocity of the steam is C1, enthalpy H1, pressure P1, temperature T1, and we are assuming that the length of the nozzle is very small. So, this is L, and if it is short nozzle, then we can ignore the change in elevation. So, if the outlet conditions are velocity C2, enthalpy H2, pressure P2, temperature T2, specific volume V2, specific volume V1. Now, steam is having high enthalpy at the inlet of the nozzle, and that enthalpy should drop, and at the cost of that drop of enthalpy we are getting high velocity. So, now if we try to look at what is, so the objective is to get high velocity. So, if we try to mark it, so our objective is to get the velocity of steam leaving the nozzle should be high, so that the kinetic energy will be higher. Higher is the kinetic energy, higher will be the momentum transport to the shaft of the runner, and that eventually produce higher amount of work output from the turbine. So, this quantity is very important and to have, because still we are having some velocity at the inlet of the flow nozzle and we are having high enthalpy as well. So, H1 is much greater than H2 and C1 is much less than C2. So, these two quantity, we are playing with these two quantities using this device and with an objective of having higher C2 at the exit. So, higher velocity of steam at the exit at the cost of the reduction of enthalpy at the exit. So, the entire objective is to have high kinetic energy. If we write it per unit mass flow rate of steam, so kinetic energy of steam at the exit of nozzle, this is half C2 square. This quantity is per unit mass, right. So, higher is the C2, higher will be the kinetic energy. So, now question is, first let us look into the change in velocity of steam as it passes through the nozzle. Question is, while we are talking about the efficiency of the flow nozzle, that means we need to look at the change in velocity of steam as it passes through the nozzle vis-a-vis the drop in enthalpy of steam as it flowing through the nozzle. So, if we go to the next slide, so change in velocity of steam, that is C2 from C1, and this change in velocity we are getting at the cost of the enthalpy drop. So, now let us look at the steady flow energy equation. So, we are writing SFEE steady flow energy equation, and then we can write why, because nozzle efficiency, that means we are having enthalpy drop, that is the heat drop. At the cost of that heat drop or enthalpy drop, we are getting the kinetic energy. So, basically energy is getting converted from its one form to the another, from its one form to the another form. So, this conversion, if we try to write how much fraction of, so what is the fraction of kinetic energy that is available at the exit of the nozzle, and what is the amount of kinetic energy, and that kinetic energy is what fraction of the enthalpy drop. So, that is what is important while someone is designing the nozzle. So, now if we write it and if we ignore the heat and work interaction, because already we have discussed that if we go to the previous slide, we can see that there is no heat interaction, and their work is essential, because to maintain a flow, to maintain the flow in the presence of pressure, we need to provide work, but that work is already taken into account in the enthalpy that you have studied in thermodynamics course. So, basically if we write it in absence of heat and work interaction, we can write C1 half C1 square plus H1 plus GZ1 equal to half C2 square plus H2 plus GZ2. And as we have assume that the nozzle length is short, so that the change in elevation can be neglected. So, what we are left with? We are left with C2 square minus C1 square divided by 2 equal to H1 minus H2. So, what we can see from this particular equation, that we are having this change in velocity at the cost of the enthalpy drop, right. So, if we go one step further, so that means to arrive at this equation, we have assumed that change in elevation of two sections of the nozzle is negligible. So, then we can write that is C2 square minus C1 square by 2 equal to H1 minus H2, and since C1 is much greater than C2, C1 is much less than C2, from this particular equation we can write C2 equal to twice into H1 minus H2 under root. So, this is the velocity of steam at the exit of the nozzle, right. So, this is the, so higher the enthalpy drop, if we can design the nozzle in such a way that there will be higher enthalpy drop, we can maximize this quantity, which in turn will ensure that the kinetic energy of jet which is available at the exit of the nozzle that is at the inlet to the turbine blade will be high. We will be discussing this particular aspect again when we shall discuss about the steam turbines. So, now question is, this is, mind it, this H 1 minus H 2, that is kilojoule per kg. So, if we go one step further, then we can write. So, that means we can write here that gain in kinetic energy, okay, between any two sections, right, of a nozzle, this is equal to loss of enthalpy of fluid or simply enthalpy drop of flowing fluid. So, the fluid which is passing or flowing through the nozzle, the enthalpy drop of that particular fluid is nothing but the gain in kinetic energy of the kinetic energy of the fluid which is between any two sections of the nozzle. Okay. So, now we can go right one step further, that is, so that is we can write C 2 equal to 2 into delta H, and that is kilojoule per kg within that is under root. So, now we can write it, what is the, so this is not in terms, so we need to convert it because this is velocity. So, our objective should be write the right hand side, the quantity which is given which is there in the right hand side in terms of in the unit of meter per second, that is velocity unit. So, unit of velocity. So, that is 2 into 1000 into delta H into joule per kg. So, what is joule per kg? So, if we go one step further, so this joule per kg, that is Newton meter per kg, right. So, that is we can write kg meter per second square meter divided by kg. So, that is meter square per second square. So, if we write here, that is C 2 equal to 2000 into delta H meter square per second square under root. So, that is nothing but 44.72 under root delta H meter per second. So, this is C 2. Why I am doing this? Because when we shall solve numerical problem, we will be using this formula frequently. That is why I have derived the expression of velocity in terms of the enthalpy drop, because I will be frequently using, that is 44.72 into delta H under root delta H. So, this is the velocity. Now, let us look at, so when we have derived the equation, when we have analyzed the flow through the nozzle, we have assumed that the flow can be modeled by an isentropic process, but in reality the frictional effect cannot be ignored. So, let me tell you, if we go back to the slide, so we have assumed that there is a flow of a fluid which is steam, and we have assumed that it is a compressible fluid, and we have also assumed that the flow can be modeled by an isentropic process. Though there is no heat loss from the flowing stream to the surroundings, because walls of this nozzle are insulated, but still we cannot ignore the frictional effect. so long as the frictional effect is there, it is very difficult to model the flow by an isentropic process. So, it is not the isentropic process. So, why? Now, question is, if the process is not isentropic, then if the process is not isentropic, say I am using different colors. So, this is enthalpy. So, if the process is not isentropic, then frictional heating will be there. If that heating is there, then the enthalpy at the exit of the nozzle should not be H2, it should be H2 prime. So, the enthalpy drop, that is H1 minus H2, that we have assumed, and assuming that enthalpy drop, we could write the expression of velocity at the exit of the nozzle using this formula, but that should not be the case, because accounting for the effect of friction that would be there in real application, the enthalpy at the exit of the nozzle will not be H2, it should be H2 prime. So, we are assuming that enthalpy should be something else, not H2. So, at what would be the enthalpy, that is very important to know, and since the enthalpy drops should not be delta H, that is why that particular term is coming into the picture, that the nozzle will also have some efficiency. That means, ideally you are thinking, we all are thinking, okay fine, if the enthalpy of steam at the inlet is H1 and we are assuming that the enthalpy of steam should be H2, and that would be obtained from any Mollier diagram, because the process is isentropic. But as I told you, frictional effect we cannot ignore, we can try to minimize, but we cannot ignore. So, considering the frictional effect, it will not be practical to model the flow by an isentropic process, and hence the enthalpy at the exit of this nozzle should not be H2, rather it should be H2 prime. So, that means actual enthalpy drop will be something which is lesser than the ideal enthalpy drop, and considering this aspect, nozzle efficiency will be there. So, let us now look into that particular fact. Say consider a frictionally restricted expansion. So, if we consider say frictionally so let me write here again. Consider the expansion of steam with friction. That means not isentropic, right. If it is not isentropic, let us look at the HS plane, HS diagram. So, this is HS diagram, Mollier chart, Mollier diagram that you have studied. So, this is very useful diagram in the context of the calculation of steam properties, because from the same chart we can calculate the specific enthalpy, specific entropy for any given pressure, temperature and dryness fraction. So, this is very useful. So, now if we try to plot the process which is there in real flow, when that real flow is taking place in a nozzle. So, if we write, so this is basically, say this is 2 pressure, because when there is a flow through a nozzle, say if we consider the nozzle is like this and this is section 1 and this is section 2, right. So, when there is a flow, we are assuming that the inlet pressure is fixed, outlet pressure is fixed. So, for the given inlet and outlet pressure, Okay. What we can do, you know, we can write this is P1, say this is P1 and this is P2, right. Say this is x equal to 1 line, right, and we are assuming that this is the expansion. So, if we try to write it, say this is the point. So, this is isentropic expansion, this is isentropic expansion. So, this is point 2, this is point 1. So, these two are the constant pressure lines and this is the line of dissection, that is x equal to 1. So, now question is, we are assuming that the flow is, so this is the flow when there is no friction, isentropic process, and that is what we have used till now to model the flow through a nozzle. But in reality what will be the case, we will be having some sort of irreversibilities and this should be 2 prime. So, you can understand that from this particular case, so 1 to 2 prime, that is the process in real application, real flow, and 1 to 2 is the so this is the actual flow or real or actual flow, and this is the ideal flow, right. And we can say that the H2 prime is greater than H2. So, now if we assume that stream of having constant enthalpy at the inlet to the nozzle. So, if P1, H1 and P2, these 3 are fixed. If these 3 properties are fixed, so we know that the expansion will take place between these 2 pressures. So, when someone is designing the nozzle, he or she knows that this is the pressure drop, and the designer also knows the enthalpy at the inlet, and then we can see that the actual enthalpy drop H1 minus H2 prime is lesser than that the enthalpy drop due to ideal flow. So, the actual enthalpy drop is lesser than the ideal enthalpy drop, and hence if we try to write it, so delta H actual is less than delta H ideal. If delta H actual is less, then the velocity of steam at the exit of the nozzle will also be less, and that is very important. Okay. So, now let us quickly see, till now we have discussed about the frictional. So, by how we can realize, by how we can visualize the effect of friction on the flow when that flow takes place through a nozzle. So, the effect of friction can be visualized on number 1, decrease the heat drop. Decrease in the heat drop. Right. Number 2, increase in enthalpy at the exit of the nozzle. right. Number 3, what we can see? So, enthalpy is increasing because H2 prime is greater than H2. Similarly, we can write S2 prime is greater than S2. So, the effect of friction can be visualized in, rather I mean if we try to discuss here, that the effect of friction can be visualized on the decrease in the heat drop, increase in enthalpy at the exit of the nozzle, similarly increase in entropy at the exit of the nozzle. So, this effect is realized not only on the decrease in heat drop, but also increase in enthalpy at the exit of the nozzle, increase in entropy at the exit of the nozzle, and finally, we also can write, see, we all have studied in fluid mechanics, if frictional heating is there due to viscous dissipation, that heating is there due to frictional effect, that is viscous dissipation heating, viscous heating, the temperature of fluid will be increased. So, now if we consider that the frictional effect is there, that heat due to frictional effect will increase the temperature of steam at the exit of the nozzle. So, that means exit steam temperature will increase. And finally, very important point, see, basically the point 2 prime is closer to the x equal to 1 line. I have drawn x equal to 1 line only to indicate that it is because of the enthalpy increase, entropy increase, the steam temperature will increase. So, that means steam will be closer to the saturated steam. So, the dryness fraction of steam will increase. Maybe let me discuss here. So, dryness fraction of steam will increase, right. So, question is, maybe we are not getting, we are getting lesser velocity of steam at the exit of the nozzle, but considering the frictional effect, we are not getting the velocity that we are supposed to get, but we can increase the steam quality at the exit of the nozzle, that is also very important considering the turbine blade erosion problem, and also the that what I am telling, steam temperature. So, this steam temperature or dryness fraction, these two are almost interrelated. Fine. Now, question is, what we have understood, that C2 prime is much less than C2. So, this is the flow velocity of steam at, or actual flow velocity of steam at the nozzle exit, and this is ideal flow velocity steam at the nozzle exit. So, C2 is not equal to C1, C2 prime not equal to C2, and it is because of this reason one coefficient is defined, that is called velocity coefficient, that is symbolized either by psi or kn. In some books it is symbolized, the velocity coefficient is denoted by psi. There are a few books wherein the velocity coefficient is denoted by Kn, and that is nothing but C2 prime divided by C2. So, you can understand the velocity of steam which is what is available at the exit of the nozzle in actual condition is always less than the ideal condition, and ratio of these two velocities is known as velocity coefficient, and the velocity coefficient magnitude is 0.93. So, Kn or psi, this varies from 0.93 to 0.97 for different surfaces. So, depending on the why this value is changing from 0.93 to 0.97, it depends on the surface of the nozzle. So, inner surface of the flow nozzle, depending on the surface condition, the value varies. Okay. So, now coming to that important point, that is nozzle efficiency. In fact, we started our discussion on this particular terminology, that is nozzle efficiency. So, nozzle efficiency, because nozzle is a mechanical device in which there is a conversion of energy, that is the heat enthalpy changes. So, at the cost of the reduction of enthalpy of the flowing stream, we are getting kinetic energy. Now, suppose we are telling that this should be the enthalpy drop, and at the cost of that reduction, what would be the change in kinetic energy, that we can get from the steady flow energy equation. But accounting for the possibility of having, not possibility, rather accounting for the essential effect, that is fluid friction, the actual gain in kinetic energy will be always less than the ideal gain in kinetic energy, and that is how the nozzle efficiency is coming into the picture. So, the nozzle efficiency, let us now try to describe it instead of writing, because we need to write the mathematical expression, but instead of writing the mathematical expression first, let us now try to look at it from the graphical representation of the flow process in HS plane. So, if we try to go for the graphical representation of the flow process in HS plane. So, graphical representation of the flow process in a nozzle or let me write here in HS plane. So, flow of steam through nozzle. We are trying to represent the flow process in HS plane. So, let us now okay. So, if that is the, this is H, this is S, and this is H plane, HS plane. What I told you? I told you that P1, H1, P2, these three quantities are fixed. So, if we have, this is the P1 and this is the P2. Okay. So, this is P2 and this is P1, right, and say we are taking one particular point over here, that is point 1, and if we try to map the process 1 to 2, so this is 2. So, that is isentropic process, that is the ideal process, but in real application the process would be like this. So, this is 2 prime, right. So, now this is basically you can see this is H2 prime, this is H1 and this is H2, right. So, basically you know that this is basically right, this quantity is H1 minus H2. So, this is H1 minus H2, that is C2 square minus C1 square divided by 2, right. And what about, and say this is right. So, this is H1 minus H2 prime, that equal to C2 prime square minus C1 square divided by 2, right. So, this is what we can write, and what we can see that, so because of the fluid frictional effect, thermodynamic irreversibility will be there, and it is because of the irreversibilities. So, basically if we try to write, this is S2 and this is S2 prime. So, we can see that S2 prime is greater than S2 and H2 prime is greater than H2. Now, so basically what is the nozzle efficiency? Ideally we are supposed to get this is the change in velocity because of this enthalpy drop, but in real case we are getting something else. So, the ratio of these two quantities is the nozzle efficiency. So, though whenever someone is designing the flow nozzle, considering the fact that the pressure at the inlet and exit of the nozzle, that pressures are equal, pressures are fixed. So, someone is designing the flow nozzle. Enthalpy of steam at the exit of the nozzle is also fixed because that is coming out from the boiler. So, knowing all these three quantities, if we map the process in this HS plane, we can see that the point 2 prime is going closer to x equal to 1 line, dryness fraction becomes higher, steam temperature increases because of the frictional effect, but at the cost of that particular favorable aspect we are going to have compromised velocity at the exit of the nozzle. So, velocity of steam at the exit of the nozzle is less, and hence the nozzle efficiency eta nozzle, that is defined as the very important term, that rate of actual heat drop. So, basically rate of actual heat drop or enthalpy drop. To that rate of actual heat or enthalpy drop, to that due to isentropic process. So, rate of heat or due to isentropic process. Okay. That means, we can tell that nozzle efficiency is defined by as the ratio of the actual heat drop to that due to isentropic process. In other way, this is nothing but the actual enthalpy drop to that due to isentropic process. So, this is the nozzle efficiency. So, if we try to write, what we can write? We can write that this actual rate of enthalpy or rate of heat drop, actual heat drop, that is H 1 minus H 2 prime, and this quantity is H 1 minus H 2, right. So, basically if we write and we also if we ignore the effect of C 1. So, basically I mean what we can write it, if we write over here, say that means this eta nozzle equal to C 2 prime square minus C 1 square divided by 2 into 2 divided by C 2 square minus C 1 square. So, that means it is coming like this, because we have agreed that this is C 2 prime square divided by C 1 square C 2 square, because so this is C 2 square, because question is C 1 is much less than C 2. So, that means the nozzle efficiency eta nozzle, that is nothing but C 2 prime square by C 2 square, that is psi square or k n square. So, that is very important, psi square by k n square, where psi or k n is the velocity coefficient that we have defined. So, if we try to summarize today's discussion, that we have tried to discuss about nozzle efficiency. First, we have discussed why this particular terminology, why this particular aspect is coming into the picture. We have discussed that since nozzle is again a mechanical device, there is a flow of steam, and to model the flow we had assumed that the process can be described by an isentropic process, but in reality the frictional effect cannot be ignored. Accounting for this frictional effect, we have tried to map the process in the HS plane, and we have seen that the gain in kinetic energy, that is due to the drop in enthalpy, in actual case is always less than that the ideal case, and it is because of this reason we can define one efficiency, and that is known as nozzle efficiency, and we have expressed the nozzle efficiency in its mathematical, I mean we have mathematically expressed the nozzle efficiency, and we have seen this is nothing but the square of the velocity coefficient or velocity coefficient. So, with this I stop here today, and in the next class we shall solve one numerical problem, and we shall see what are the several factors that affect the nozzle efficiency. Thank you.